Okay, today we'll start another part of linear programming lecture, graphical method. This is the part 2, and in previous class we have studied about linear programming problem and as an introduction. Now today we'll discuss about the graphical methods. Um, Actually, this is the connection. There is a connection between previous class and in this class, and this is the second part of this. So in previous class we have studied more about linear programming. What is linear programming, why we are using linear programming problem, actually what's the application of this linear programming in business, economics, and in industry, in engineering also. In different parts, there are huge parts of linear programming, and we have discussed about the background of linear programming. Okay, background, what was actually World War II was the actually background of linear programming, and the purpose of linear programming we have studied. What was the advantage of linear programming actually, we have studied, and we have studied also the graphical methods, how to solve linear programming by using graphical methods. Now today is also graphical methods, and part 2. Now the graphical solution, how to find the actually solutions of a graphically by of a linear programming models. Okay, there will be only two decision variables, one is x and other is y. The graphical methods provide visualization of how a solution for a linear programming problem is obtained. Actually we'll use here corner methods for finding a linear programming problem. This is actually the method iso profit. In actually business, we use iso profit or cost, how to minimize the cost of a model. And the extreme point, finding the extreme point evaluation method, where we have to use graphical methods for this. Now suppose we'll study about another problem. Okay, how to solve graphically the minimization problem. In previous class we have studied. Now another example too, a maximization problem. Okay, a maximization problem, how to solve a maximization problem by using graphical methods. Now maximum z 5x1 plus 7x2 with subject to the constraints x1 less equals to 6, twice x1 plus 3x2 less equal to 19, and x1 plus x2 less equal to 8. And where this is actually non-negativity restriction, and these three are constraints or limitations. Okay, and this is the actually what objective function. Maximum z equals to what, 5x1 plus 7x2 is the objective function, and these three are constraints, and this is the non-negativity restriction. This whole makes a linear programming problem, remember it. Now we are trying to solve this. Actually there are decision variable two decision variable, one is x1 and other is x2, right? There are three constraints. How many constraints? Three constraints. Now if we take the graphically, take this first, x1 equals to 6, right? First inequality, x1 equals to, remember it, for maximization problem we must take this then less equal to, okay, this sign. For minimization problem, greater equal to, remember it. Okay, remember it. So x1 less equal to 6, that means after putting x1 equals to 0, x1 equals to 6, this is the first constant. Okay, x1 equals to 6, just 6, x equals to 6, in x axis x1, and in y axis x2 variables. Okay, so first constant will be this, just putting x equals to what, 6, we get the straight line parallel to the y axis, right? This indicate what, x1 less equal to 6. Now for the second graph we can take, for the second graph, what one, x2 equal to, if x2 equal to 0, x1 equal to what, 19/2, right? 19/2. But if x1 equals to 0, x2 equal to what will be, 19/3. Now we can plot this like this. One is 19/2, right? 9.5. Then this will be 0 into 6 and 1/3. Okay, this is the twice x1 plus 3x2 less equal to 19. One is, uh, if we take x2 equal to 0, then x1 equal to what will be, 19/2. That means less than 10. Okay, less than 10. This is the 19 by 2. Okay, 19 by 2 comma 0, and this will be 0 into what will be 19 by 3. Understand? Or 6 and 1 by 3, same ones. Just more than some, more than slightly maximum. Okay, slightly more. Okay, more than 6. So this is the second quadrant, second constant. And this is the third one, x1 plus x2 equal to 8. So if x2 equal to 0, then x1 equal to what? 8. Then we get this point 8 0. If we put x1 equal to 0, x2 equal to what? 0. So we get another 0 8 point. Just adding this, we get the third constant. Okay, so combinedly we get three constant like this. This is the first constants, and this is the second constants. Okay, 19 by 2 and 19 by 3. Okay, and this is the third constants. Understand? This is the third constant. So we get after graphing, after plotting three constants in a graph, we get these types of graph. Actually here there are three corner points for maximization problem. For maximization problem, corner points will be this. How many corner points here? 1 2 3 4 5. Actually this is the 1 2 3 4 5. This is the corner points, right? This is the feasible region for maximization problem. Understand? Just opposite of minimization problem. In opposite, there were there are opposite to origin. In minimization problem, the feasible region will be opposite to origin. Understand? Origin means what? 0 0. But in maximization problem, directed to origin. Okay, this will be the feasible region. How many corner points here? 1 2 3 4 5. Actually these points is the intersection point of what? Constants. Constant 2 and 3. Okay, constant. And this is the this intersection point of constants. Which one? 1 and 1 and what? 2. Sorry, 1 and 3. Okay, 1 and 3. This is the intersection point of 1 and 3. After solving this, we get this point, and after solving this intersection point of what? 2 3, we get this intersection point, and this is known 6 0, and this is also known, and this is 0 0. Okay, so we get this. There are how many corner points? 1 2 3 4 5. Okay, these 5 corner points. Understand? And these corner points will give the corner points. These corner points will give the intersection point of what? Actually these corner points will give the intersection point of 1 and 3. Okay, intersection point of constant 1 and 3, remember it. And this is the intersection point of what? 2 and 3. Okay, so we, after solving 6 2 and 5 3, we get the result. So having identified the feasible region for the problem, we now reach for the optimal solution. That means we are maximizing the objective function, which will be the point of the feasible region with the largest in case, because maximization, or the smallest in case of minimization problem of the objective function. To find this optimal solution, we need to evaluate the objective function at each of one of the corner points of the feasible region. There are 5 points actually. Okay, one is 0 0. Z equals to what will be? Just putting x1 equals to 0, y1 equals to 0 in this objective function. X1 equals to 0 and x2 equal to 0, what will be? Maximum Z equal to what will be? 0. Okay, now if 0 6 0, another one is this point was what 6 0. So x1 equal to 6 and 0, x2 equal to 0 in objective function will give Z equals to what? 30. And this is the 6 2. After solving 2 and 3 constants, constant 2 and 3, we get uh, 2 and 3, we get 6 0, 6 2. 6 2 will be the 44 maximum Z. X1 equals to 6, x2 equal to 2. Just putting in objective function, we get 44. Another point 5 3. 5 3 is the corner point. After solving what? 2 and 3. After solving 2 and 3 constants, so we get 5 3, and this 5 x1 equals to 5, x3 x2 equal to 3, and putting this in objective function, we get 46. And last corner point, this is the actually what? 6 19 by 3, 0 19 by 3, so 44.33. That means what? Which is the maximum here actually? 46. So maximum value of z we are finding 46, and these 46 found for this point what 53. This is the optimal solution, optimal solution of this. This is the optimal solution, and this is the 53. Okay. So extreme point and the optimal solution. The corner or vertices of the feasible region are referred to the extreme points. Here how many? How many corner points? 5 corner points. Okay. This is also called extreme points. Extreme points of the feasible region, or corner points of the feasible region. Feasible region where? Where in which region we have solution. We will find the our solution for the maximization problem. This is the actually connected with origin, remember it. But for minimization problem, this region will be opposite to the what? Opposite direction, in opposite direction. Feasible region will be in opposite direction. So we get an optimal solution to the linear programming problem can be found at the extreme points of the feasible region, actually by corner method. When looking for the optimal solution, you do not have to evaluate all feasible solution points. You have to consider only extreme points of the feasible region. Now actually what is feasible region for this linear programming problem? The feasible region of two variable linear programming problem can be non-existent, a single point, a line polygon, or an unbounded area. Actually these types of area. Okay, this is the pentagon actually. Okay, these 3, 4, 5, this is actually pentagon, and this may be any unbounded area or any polygon. Polygon means pentagon, hexagon, okay, triangle, etc. A line may be also, okay, a single line also. So any linear programming fails in one of the three categories, remember it. This is the limitation of linear programming. So it's me and infeasible, that means there is no feasible region, that means there is no solution. Has a unique optimal solution or alternative optimal solution, that means more than one solution, may have more than one solution, and has an objective function that can be increased without bound. Okay, there may be another characteristics of objective function which will be increased without bound. A feasible region may be unbounded, and yet there may be optimal solution. This is common in minimization problem and is possible in also maximization problem. So in a special case, actually, alternative optimal solution, infeasible, unbounded, etc., may be possible. Suppose example with a multiple optimal solution. Multiple optimal solution. There is actually fixed. There is fixed, no fixed region, feasible region. So for this minimization, maximization problem, subject to the constraints are 2 here. Okay. Actually, there are in this case we can draw this. Okay, this 2 straight line only 2 straight line. Just we get this is the less equal to and this is less equal to. Now if you want to solve this optimal problem, maximization z equals to twice x1 plus 6x2, subject to the these two constraints, remember it. One is less equal to, another is what? Greater equal to, remember it. But in maximization problem, all symbols will be what will be? All symbols will be what will be? Less equal to, remember it. But in minimization problem, the sign will be what? Greater equal to. Now let us try and try to solve another problem. So, and this example, a small scale electrical laboratory industry, and there are two skilled men. Skilled man is X, and skilled women are what? Women will be number of in Y. But the total number cannot exceed what? 11. This is the constraints, remember it. And another salary will not more than taka 60,000 per million. Okay, so male workers are 6,000 and female workers are 5,000 paid. Okay, and data collected for the performance. Now data dedicated male members contributes taka 10,000 and female members contributes taka 8,500. Remember it. This is the actually objective function for us. If there are x person male, and if there are y person female, then total return will be what? 10,000 into x plus 8500 into y. Okay, this will be the objective function. Now you have to determine the number of male and female for this data. So the for the first step, formulate the problem. Objective function will be what? Let number of male will be x and number of female will be what? Y. So maximize. We have to maximize the z, contribution of male members plus contribution of female members. Actually, there are 10,000 per man and 8,500 per female. So total number will be 10,000 into x plus 8,500 into y. This is actually we have to maximize the return. That means to maximize the look like profit. Now subject to the constraints. First constraints, the number of women, total number of women cannot exceed 11. That means what? X plus y of course less equal to 11. This is the first constraint, right? And second constant 6 per man 6,000, okay, and per female were 5,000 and cannot exceed 60,000, okay. This is the constant 2. Understand it? 6,500, okay, paid 6,000 and paid 5,000. 6,000 into x plus 5,000 into y, okay. But salary bill not more than what? 60,000. This is why 6,000 x plus 5,000 y less equal to 60,000 per million. Understand? So there are two constraints. Now now step 2, we have to plot this plot these constants into graph. Now let number of male workers x be the horizontal axis, okay, horizontal axis. That means was in y axis, and number of female will be in male will be in x axis and female will be in y axis. Understand? Vertical. Now plot the constraints. To plot the constraints, we will up to an arbitrary value of the variable. Suppose this is the first constraint, x plus y less equal to 11, and converting this is the this inequality to equality equation. Okay, we are converting this as what? Equality equation. Now we will take this. This is a table, one for x, another for y. Just to putting y equals to putting x equals to 0, we get y equals to what? 11. Putting y equals to 0, putting x equals to 0, we get y equals to 11, and putting y equal to 0, we get x equals to what? 11. So there are 2 points. One is 0 11 and other is 11 0. Now for second constraints, converting this inequality to equality equation, then putting just dividing with what? 1000 maybe. Okay, dividing by 1000, we get this. So for x equals to 0, 5y equals to 60. That means y equals to what? 12. Now if y equals to 0, then 6 is equal to what? 60. So x equals to what will be 10. There are another 2 points. Now for the first constraints, this is the actually x axis and this is the y axis. This is for male and this is for female. So first point was what? 11 0. Okay, this is the 11 0, and along y axis 0 11. This is the 11. Just joining this, we get the graph of what? First constraints. Now for the second constraints, now male for this x-axis on male 10 0 and another is 0 12. Okay, 10 0, another is this is the 10 0 and this is the 0 12. Understand? This is the second constraint. Just plotting. And this is the this is for inequality. If less equal to, remember it, we have to plot in the direction where origin. Okay, okay, this will be the feasible region for this constraints, and this will be the feasible region for this constant. Remember it. Less equal to means what? Directed to origin. Remember it. Opposite according to the origin. Now find the optimal solution. Combining these two constraints, we get the feasible region, and this is another point of intersection of these two of the given constraints. This is the intersection point. So there are 3 corner points. One corner point, another corner point, this corner point. Okay, and this is the origin corner point. How many? 4 for this problem. And this is called what? This is called feasible region. In this feasible region, there are 4 corner points. So this is the only feasible solution, optimal solution point. And this is the number of male. This is the number of female. Now we are circle potential optimal points. Actually there are potential point, how many? Four corner points. Okay, one is this, and 5 6 comes from what? Solving the constraints, two equation, solving these two equation. Okay, we get 5 and 6. This is the corner point, and these 4 points are optimal, extreme points, also extreme points, remember it, for the maximization problem. Now we are tabularizing these potential points or extreme points. Okay, extreme points will be 0 0, 4 points actually, 0 0 0 11 5 6 10 0. These 4 points comes from this. Okay, these corner points, 4 corner points. Now z equals to what was 10,000 x plus 8,500 y. This is the objective function. Okay, objective function. After putting x equals to 0, y equal to 0, we get this, and maximum z is what? 0. After putting x equal to 0, y equals to 11, we in this objective function we get this, and will be 93,500, and 5 6 x equal to 5 6, y equal to 6, we get this objective function equal to what? Will be 1 lakh 1000. Okay, after putting 10 0, then we x equal to 10, y equals to 0 in the objective function, we get this, and total maximum z will be what? 1 for this point, 1 lakh. So the maximum z obtained at what? 1 lakh 1000. That means at this point, this is the actually optimal point for this problem. Understand? This is the result. So maximum z equals to 1000, 1 lakh 1000 at x equals to 5 and y equals to what? 6. So now total number of male will be 5, and number of female will be 6. Now solve the following linear programming problem graphically. Minimize and maximize z equals to x plus twice y. This. How many constraints here? 3 constraints. Huh? And this is the non-negativity restriction. There are 3 constraints, and this is the what? X plus twice y is the what will be objective function. Remember it. Now we have minimize or maximize this x plus twice y subject to the constraints. There are some greater equal to, one greater equal to, and another is less equal to, and this what? Less equal to. Now converting the above inequality, we have the equality equation. Just converting equality. X plus twice y equal to 100, twice x minus y equals to 0, twice x plus y equals to 200. Just this is the non-negative restriction, can be written as also what? Converting to equality equation. So now drawing this for the first equation. If x equals to, y equals to 0, then x equals to 100, and if x equals to 0, then y equals to what? 50 from the first constraint. Okay, from the first equation. That means a point this and b point this. Okay, you can tabularize this like this also. Just making a point 100 0 a and 0 50 will be what? B point. So we can draw this. We can draw the line. This meets the x-axis at 100 0 and meets y-axis at 0. This is the first point. This is the first constraint. Okay, this is the first constraint. Remember it. Now another region represented twice x minus y less equal to 0. Okay, twice x minus y, the line twice x minus y passes through the origin. Remember it. Passes through the what? Origin. This is the second constraint, right? Passes through the origin, y equal to mx types equation, right? This is the second constraints. Understand? And intersect at what? Intersection point. There is intersection point between first constraint and second constraint. Now for the another twice x plus y less equal to 100, another constraint, third constraints. Okay, we get making this box x equals to x and y. If y equals to 0, then x equals to 100. Okay, and if x equals to 0, then y equals to what? 200 for this constraint, right? So this is the for third constraint, right? X equals to 100 0, x equal to 100 here, and y equals to 0, and x equals to 0, y equals to what, 200, and this is the actually what, third constant. Now this is the actually feasible region. Okay, this is the feasible region. In this region first line, first constant, second constant, and third constant are exist. Understand? So the region represented by this, we can get the corner points. What, there will be 4 corner points actually. What, this corner point, this corner point, this corner point, and this corner point. There are 4 corner points, and this is the intersection point between first constant and second constant, right? And this is the intersection point of second constant and third constant. Remember it. Just solving second and third, we get this d, and solving first and second constant, we can get this e point. Okay, so corner points of the feasible region b c d e b, b c d e b, b c b c d e. Okay, we get this 0 50, 0 to 100, 50 to 100, 20, 40. So maximum that after putting x equals to 0 and y equals to 50, we get 100. After putting x equals to 0 and y equals to 200, we get this. After putting x equals to 50 and y equals to 100, we get this. Okay, so maximum what here, maximum z 400. Okay, and 400 obtained at what, c point, right? And minimum value of objective function will be what, only 100 this, but only 100 this, but this is the actually 0 here, x is 0, so only acceptable point is this 20 40. Understand? Solve the graphically the following linear programming problem to minimize the cost. Z equals to 3x thrice x plus twice y subject to the following constants. This greater equal to greater equal to greater equal to. Okay, this is the actually minimization problem. This is why greater equal to. Now minimization objective function this subject to the constant this. So this is the given constants, and this is the non-negativity restriction. Now converting this inequality to equality equation. Okay, just from first constant we get this, from second constant this, from third constant this. Okay, now drawing the graph for the first inequality, that means first constants, x comma y points. Just this is the putting y equals to 0 here, x equals to what, 2. After putting x equals to 0, y equals to what, 10. Okay, 0 10, and this is the 2 0. This is the first point a, and this is the second point b for this, for the first inequality. Okay, similarly for the second constants, x and second equality equation, we get this point c and d. Okay, after putting y equals to 0, we get y equals to 0, x equal to 6, and if x equals to 0, then y equals to what, 6. This is the point c and d. Okay, now again and third constants, and from the third equality equation, just ef point. Okay, after putting y equal to 0, we get x equals to 12. If we put y equals x equal to 0, then y equals to what, 4y equals to 12. That means y equals to what, only 3. That means e point is the 12 comma 0, and f point is the 0 comma 3. Now plotting these three constants. Okay, this is actually first constant, which one, first point 2 0 0 10, 2 0 0 10. This is the first constant, right? 5x plus y 10, this is the first constant, and the shaded in higher, opposite to the direction. Okay, shaded will be higher, opposite to the origin, opposite to the origin, because greater equal to, remember it. Now for the second case, x plus y equals to 6, this is the x plus y equals to 6. That means 0 6 6 0. This is the 6 0, and this is the 0 6. Just joining this, we get second constant. This is the second constant, remember it. And this second constant, shaded region higher, opposite to the what, origin, opposite to the origin. Then for the third constant, 12 comma 0, 12 comma 0 is this point, and 0 comma 3, that means this x0 and y3. So joining, this is the third constant. Okay, third constant. So shaded region higher will be shaded opposite to the direction. Okay, opposite to the origin, opposite to the origin, because this inequality is greater than or equal to 0. So the shaded region will be this. How many corner points here? 1 2 3 4. Remember it, for minimization problem, Shaded region will be opposite to the origin. This is the opposite. This is the origin and opposite here. So how many corner points? 1, 2, 3, 4. Actually, there are two intersection point. One is Z and other is H. Okay, Z is the intersection point of what? Constant 2 and 3. Okay, constant 2 and 3. Solving equality equation 2 and 3, we get 4 and 2. And again, the intersection point H from where? This is the intersection point of 1 and 2. Okay, 1, 2 constant. So we get and the corner points this. Okay, corner points how many? E, Z, A's, B. Okay, solving Z point is solving what? Constant 2 and 3, and H point constant 1 and 2. Remember it. Just solving on 1 and 2 equality equation, we get these 2 points. Now corner points will be this, and putting in objective function, we get this. This equals to, which was in minimum here, 13 is the minimum. So 1, 5 is the best extreme point for us, and this is the optimum point, where minimum occurred. Okay, so the S is the minimum value when x equals to 1 and y equals to 5. So x equals to 1 and y equals to 5 is the optimal solution of the given linear programming problem. Hence z is the minimum when x equals to 1 and y equals to 5, and the minimum value of z will be what? 13, because minimum. Very easy for you. If you can solve, I hope every maths are same for you. Okay, solve the graphically the following linear programming problem. Maximize z subject to the constant this, and this is the non-negativity restriction. This is homework for you. First of all, you have to convert inequality to equality equation. Okay, then draw the graphs. How? Just making this table. Point I will be this, putting y equal to 0 in first constant and putting x equals to 0 in y equals to 300. This is the point B. For the second constants and second equality equations, we get C and D point. Okay, now we can plot these 2 points. Understand? Okay, next day we will try this another example, how to find iso profit or iso cost method. Okay.
जी सर.